Some of the world's largest reserves of oil and gas lie within the countries of the Gulf Cooperation Council. These countries face a unique challenge: how to maintain a strong economy based on fossil fuels, meet increasing energy demands, yet reduce greenhouse gas emissions. From the world of semiconductors to circulation patterns of the Red Sea, new discoveries are paving the way. Let's see how. Cutting-edge research by faculty and students at the King Abdullah University focus on different projects.
If you think about all the technologies that are underpinning our modern society, you realize that semiconductors are pervasive throughout our life.
We're used to materials being fabricated in very stringent environments. For example, semiconductors like silicon, they have to be fabricated in fabs and under very high temperatures and so forth. That makes them very difficult to utilize in developing countries. Even though we need a lot of these technologies, such as our phones, it makes them very difficult to be pervasive because only a few countries around the world can manufacture them.
The technique they're using takes advantage of a property called self-assembly, the spontaneous organization of components into larger, well-defined aggregates.
We're interested in materials that we could grow in our labs, inside liquids, such that they grow at low temperatures spontaneously and form semiconductors that are still very useful and have performances that make them potentially a replacement for the very expensive semiconductors being used today.
Pushing down costs is also a high priority for another research project, this time fine-tuning the pore size of crystalline materials to capture carbon dioxide.
The technology today is so expensive that we cannot do it, but that's what we do in our lab.
This technique is also more energy efficient over the long haul, and it's reusable.
There is a large development that you can control the pore size of this material to have the right functionality and the right pore size that they can selectively capture the CO2 from flue gas, which you cannot do with other materials, for example. And this is a fruit of more than 10 years of research, and the most important that the science works, and now it's just a matter of time to scale it up and get it in the process to work.
Moving from the nanoscale to the waters of the Red Sea, large-scale models hope to inform future plans for more renewable energy resources. The work began with some major data gaps.
It's one of the least studied seas in the world. Before we come to the Red Sea, there were very little known. There are still many things we don't understand about it.
One thing they do know is that global climate change is having an impact.
It's also warming more faster than the other seas. And the sea surface temperature of the sea, we're seeing changes in the wind trends, and also it's reflected in trends in the waves so far. We're expecting that this will have a very important impact on the circulation of the Red Sea.
These changes could affect locations for renewable energy projects, shipping routes, and desalination plants.
There are a lot of research now to exploit energy from wind, from solar, from waves. We're hoping that we'll be able, in the long term, not only do the Red Sea, but also extend it and include all the Saudi seas from the Arabian Gulf for the whole peninsula, and include all the system as one.
Even though these different projects may not pay off immediately, the scientists leading the charge are good at maintaining a long-term vision, fueled by a passion for the work.
It's a very exciting process when I work with the students, and every day we discover something new. And every day is different from the day before. And when we discover things that have potentially have an impact on the environment and on energy, it really motivates us to keep on going and keep on digging for the next vein of gold or the next vein of discovery.